Today we'll cover a lot of control flow handling. Remember, we left off here last time. Is everything all set? Okay, good. I got the date right there. Wait a second. Okay. Just a few reminders. You know that you're doing homework 3. This is the grade distribution for homework 2. I'm not going to cover that in detail. You can find these slides online. It's a little bit worse than homework 1, I think. So I hope it won't get progressively worse as we go into the semester. But even if you didn't get everything right, look at the solutions. I cannot emphasize enough this point here. Start early. The slide will take time. And I'll give you more detail. So optimize your design. Basically, early checkoff will buy you extra points. And also, fastest redesigns will get extra points. And exactly how we determine this will be dependent on the distribution of the fastest design. So what is the fast design? Remember, performance is, hopefully you know very well by now, what is the execution time, right? It's number of instructions times cycles per instruction times clock cycle time. We're going to test your designs with a given program, so number of instructions will be the same. It won't change. But you are able to optimize your design by optimizing these two things in your pipeline microarchitecture. So if your design achieves the lowest execution time by optimizing either of these or both of those, and if it achieves a significantly lower execution time compared to the rest of class, then I'm willing to give you up to 10% extra credit. So 10% is pretty high, hopefully. Yes?
Can you check it off in the first week, but optimize it in the second?
Yes, you can do that. Exactly. So you could actually stack the extra credits if you want. You can check off early with one design and then later keep optimizing and maybe win the fastest design prize. Right? Yes?
It's like a pipeline single cycle, right? So like even though the rate is going to be like whatever the length of the pipeline, it will still be one cycle per instruction.
Well, is that true? Think about it. It's not one cycle. It is. So ideally, it's one cycle per instruction. Right? Ideally, you would like to get a one cycle, one instruction throughput out of the pipeline. But remember, there are control dependencies, there are data dependencies, and your design, your cycle per instruction depends on how you handle those dependencies. And those are the things that reduce the CPI in a pipeline design. So you can really optimize both of these in your lab. Yes?
Can we change the multiplier to optimize?
So, no, right?
No.
Yes, the answer is no. Yes?
There's a question about the cycle labs in general. Which labs do you plan on having on the starting labs?
Which labs? It'll be the labs that come later on.
Okay.
Not this lab though.
Because I know in previous years that all of them were programming labs.
That's right. But this is a different course now. I mean, the course is the same, but a different instructor. So we will have some labs later on that are part of that. But I think it's very important for you to do the lab on your own to really learn the material. Okay? So this, I know I'm being a little bit hand-wavy here, but if you actually really optimize your design, you'll get up to 10% extra credit. Okay. So this is the lab 2 rate distribution. Most of you did quite well, actually. It's almost perfect. And the maximum is a perfect score, of course. Minimum is 81. But not all of you submitted, I think. There are more people who submitted homework 2 than lab 2. Okay. So prize for lab 1. Is Kiyong here? You're there? So you did the fastest simulator, so you get a prize. I don't know if you like reading books, but this is a great book. It's the Soul of a New Machine by Tracy Kidder describes the adventures of a design team in designing a cutting-edge microprocessor mini computer in the late 70s and early 80s. It is actually a very popular book. It's written for the general public's consumption. It won the Pulitzer Prize when it came out. So I hope you enjoy it. Well, we can put it up online on the course website too. The soul of a new machine, right? Machine, and spell machine, by Tracy Kidder. And there might be a Kindle edition by now, so this is probably obsolete. Obsolete in the sense that obsolete reading. Okay, so we'll give you a feedback sheet online. Basically, we would like your feedback on the course. I think there will be 8 questions on the feedback sheet. And I would really appreciate your feedback if you fill it out. This is not required. It won't be graded, obviously. And it can be anonymous. But if you take time and answer the questions, hopefully that'll help us improve the course this time as well as for future generations. And I would really appreciate it. I read all of these feedback sheets very carefully and try to adapt the course based on the feedback. Of course, I cannot take into account all feedback, right? If the feedback is contradictory. And there are cases where that happens. There are students who think the course is moving very fast, and there are students who think the course is moving very slow. So I try to adapt the pace, but you cannot always satisfy both ends. But I take all of these feedback sheets very seriously. Both the TAs and I will read them very carefully. So please take the time. Same with course evaluations that you will fill out at the end. I value them a lot. And well, we would like to impose a deadline, of course. We would like you to turn it in by Wednesday, February 29th, so that we can read them. You can turn it anonymously, or you can email it. Of course, if you email it, it won't be anonymous unless you decide to spam us from some random account. So, don't forget, though. I would like to get, I think, 53 feedback sheets. Midterm 1 coming up. We said March 5, but I would like to call you. We could actually do it on March 7th also. Yes, so that means you would prefer March 5 or March 7?
Yes.
Okay, so who says March 5?
It's a Monday.
And who says March 7? So it's about equal, which means that we'll go with the original date, March 5. So let me. Let me. So the reason I want to reconsider it because the lab is due March 2nd. Your third lab, which means if you start your lab too late, you will likely not be able to finish it by exam time, so you won't have time to study. That's why I'm suggesting you should start the lab very early. Are you guys still fine with March 5? Yes? Okay. No. I cannot give 2 exams, so we'll have to pick.
It's not work if you don't vote.
Yes?
I could say that, like, if you need to take a late day, that, like, if you want to take it till Tuesday, like, you get 1 late day less, and you get 1 last day.
For the lab?
Yeah.
No, well, you have only so many late days, right? So I think we will go with the original date that we set for the exam. No? Yes?
You should cut it down to 1 week term instead of 2.
So you can write that on the feedback sheet. We have to proceed with the lecture now.
Maybe that's just have people email you if they have considerations, so then you can make a more decision.
No, I think, well, we already set the date, so I'm not going to change the date now. And you'll have to take the exam. I cannot prepare multiple exams. I just want to check. Looks like people have planned for March 5. that's why we cannot change it. Yes?
In order to sway the people who are saying March 5th, if they push them back to March 7th, that strictly gives you more time to study, and you're just hurting yourself if you push it forward. The argument that you have 2 tests on one day, which means that you can't plan your time well enough to study for both.
Are you swayed? So okay, let's take the vote again.
Yeah.
Who wants March 5? you can look at people who want March 5. No, be brave. March 5? Only one person? 2? Okay, looks like you've swayed everyone. Who wants March 7? Okay, looks like people want March 7. And actually, that's a good argument, I think. So I think, so I'll change this to March 7. That gives you strictly more time to study, and that alleviates the pressure on you so that you can do your lab too. And actually, there's one more thing. We can have a review session on March 5 now.
Yes.
Okay. So March 7 Wednesday. Let's study hard. It'll be a tough exam. It won't be tougher because you said March 5. It'll be the same. Okay. One note on labs. So this is the Verilog code. I think similar to what some of you did in the lab. The question is this combinational or stateful? It's stateful because you have not specified what this variable takes for one case, right? Which means that how would you know what the value of it be in the next cycle? Well, it's implicitly a latch in that case, right? Yes.
If we declared initially to be 0, so if we say right, the first line is always add star beginning, and we say A equals 0.
It is combinational in that case, because then you fully specify and then override it with one of those cases. So this is stateful. Well, I guess I gave you the answer. Chris gave you the answer. This is his slide. So basically, you have to assign this register on every path, or every case in this case. Otherwise, it becomes an implied latch. So you've got to be careful. So you fix this problem. Well, we didn't specify it for lab 2, but in lab 3, you may not imply latches. Okay? So you need to ensure that this register is assigned for every case here, and you can do that by doing this, right? Or by doing what you suggested.
Can we expect Verilog code on these?
You can expect anything related to the lectures. Everything we cover in the lecture, lab, homeworks, they can come in exam. Okay, discussion sections. Some discussion sections are not very well attended, especially the Tuesday 10:30 a.m. section. Is that too early for you guys? Looks like there are more people who attend the Friday 6:30 p.m. section than Tuesday 10:30 a.m. section. Should we change the time of this one?
Some of the seniors have class at 10:30.
Oh, I see. Okay,
Like 2 hours would
like
probably
12:30.
yeah, like 12:30.
Okay. How about later during the day?
Yeah.
Okay. Okay, so we will probably change the time of this one, and you can figure out when the room is available. Are the discussion sections useful? That's the other question. So you can treat the discussion sections as office hours, right? You can. But you will benefit most if you go to the discussion sections and actually the TA goes over the material that I covered in lecture, and you ask questions. So I would really encourage you to go to the discussion sections, especially during the next 2 weeks. Because the exam is coming up, and you don't want to study for the exam in the last 2 days. Whereas if you go to discussion sections, Chris, Lavanya, and Abir will cover what I've covered during the lectures, and they will go over some questions as well. So you will benefit a lot from that. And we will change the time of this one. And we should probably add a question on the feedback sheet for about the discussion sections. Okay, readings for our next lecture. Next lecture, we will do more advanced pipelining, interrupt and exception handling, and we'll cover the concepts of auto-order execution and superscalar processing. So I would like you to read Patterson and Hennessy chapters 4.9 through 4.11, which covers exception handling and some auto-order and superscalar execution. And there's also the Smith and Sohi paper that goes through what a modern microprocessor actually looks like, what something like Pentium Pro or AMD K5, K7 looks like. And hopefully you'll enjoy this paper. Okay, and this will be on the website. Okay, there's a calcium seminar today. If you can, please attend. And we talk about this. It's at 4 p.m. at Hammerschlag Hall D210. So if you're in Hammerschlag, you can just stop by. And I understand there are snacks too. But first come, first serve. Okay, last lecture we covered data dependence handling, different approaches to do this. And we also started control dependence handling. We'll continue on control dependence handling. But just to remind you, there were a bunch of issues in pipeline design. We talked about balancing work. We talked about handling dependencies to ensure that the pipeline is correct, moving, and full. And we will talk a lot about how to handle control flow today. We talked about how to handle resource contention. We will talk about how to handle long latency operations to improve pipeline throughput, especially when we talk about out-of-order execution. And next lectures, we'll talk about exception and interrupt. And again, in the next few lectures, we will talk about how to minimize stalls, how to minimize cycles per instruction with concepts like out-of-order execution and superscalar execution. You already know some of this, and you will do some of it in your lab. Okay. So the basic problem with control dependence is you don't know the instruction that you're going to fetch in the next cycle while you're fetching the current instruction. Right? Because you don't even know what the current instruction is. You don't know whether you should increment the PC by 4, or you don't know whether you should jump to the target. So a very terrible way of handling this would be to stall every other cycle. Right? Such that once you decode the instruction, the previous instruction, you fetch the next instruction. But that's terrible for pipelining. That effectively you held your throughput in a pipeline, right? So this makes no sense. So what you really want to do is perhaps, instead of waiting for this true dependence on the program counter to resolve, so that you know whether the instruction is a control flow instruction and non-control flow instruction, you just guess next program counter will be program counter plus 4, right? While you're fetching the current instruction. And the next cycle you fetch the next instruction. I guess, is this a good guess? Well, we can do the calculation, right? If you assume 20% of the instruction mix is control flow, and this is actually a good number in integer applications, where you do a lot of branching, that means 80% of the time, this is definitely a good guess, right? Because 80% of the time, the next instruction is not a branch. And if you actually look at some statistics that people have collected over years, if you look at the control flow instructions, typically, well, this number changes depending on the application, but typically 70% of them are taken and 30% of them are not taken, which means that, well, 30% of 20% is 6% overall, right? So 6% of the time, the next instruction is again PC plus 4, at PC plus 4. So 86% of the time, the next program counter is really PC plus 4. So it's a very good idea to guess that the next program counter will be PC plus 4. Now the question is, what do you do for the remaining 14% of the time? It's not PC plus 4, and these are all averages, right, across a bunch of applications. And we will talk about what we do for the remaining 14% of the time in this lecture. Okay? And I'll call this the control dependence handling. And remember, well, we would like to keep the pipeline full in the presence of branch instructions. we've already covered that this is not a good idea to call the pipeline until we know the next fetch address. Guess the next fetch address. How? Well, we're going to assume that if it's non-control flow, we're going to automatically guess the next fetch address is PC plus 4, but we're going to override it in some cases. And we will most of the lecture will be about this idea of branch prediction, guessing the next fetch address, right, when you have a control flow instruction. But before that, I would like to cover some other approaches, delayed branching that we briefly discussed, doing something else, and I will get back to eliminating control flow instructions and fetching from both possible paths after we cover branch prediction. Okay, delayed branching, you're already familiar with the idea, right? The idea is, if we do not know whether or not the branch will be taken or not for n cycles, why don't we change the semantics of the branch instruction such that the branch takes effect after n instructions? Make sense? So you have a branch, and after that, you have a delay slot, if you will, and you delay the execution of the branch until all the instructions in the delay slot are executed and completed. And that's the idea. And these instructions are always executed regardless of the branch direction. The branch can be taken or not taken, doesn't matter. The instructions that come after the branch and instructions are always executed. Yes?
This is what the programmer is doing, is it something different?
This is what the programmer is doing. Yeah. So the semantics of the branch at the ISA level is that you have the branch and you have the next instruction. If this branch semantic says that you always execute the next instruction that comes after the branch, regardless of what the branch does, then you have a one instruction delay slot. And it's the programmer's or the compiler's job to fill this delay slot with an instruction that's independent of the branch, right? So you should not change the semantics of the program to fill the delay slot. And if you cannot find anything, then you fill it with a no-op. And essentially you lose throughput in your pipeline. Okay. Well, the problem is, of course, how do you find instructions to fill this delay slot? The branch must be independent of the delay slot instruction, right? Well, if this is an unconditional branch, then it's easy to find instructions to fill the delay slot, right? Because you're jumping to some location later on. Well, let's say you have a jump here, and this jumps to some code block here. Well, basically, you can put this instruction to the delay slot, right? So you don't have a problem, because this is going to be executed anyway, regardless of whether or not the branch is executed. If it's a conditional branch, well, there's no condition in this case, basically. You're not going somewhere else. But if the branch is a conditional branch, now the condition computation should not depend on the instruction in the delay slot, right? Which makes it difficult to fill the delay slot. Let's take a look at how this works. I'm going to give you an example of a two-stage pipeline. And this is the normal code that you would normally execute with a conditional branch that doesn't have a delay slot. And we're going to assume that we're going to stall when we fetch the branch. So in the first cycle, you fetch instruction. These are instructions. And branch conditional X is a branch that jumps to location X if the condition holds true. And these are the dependencies, data dependencies, that I kind of pictorially show you. In the first cycle, you fetch instruction A. Next cycle, you fetch instruction B. Next cycle, you fetch instruction C. Next cycle, you fetch the branch. Well, after the branch, assuming, let's say, we know the branch, this is a fetch decode, and then later execute write back kind of pipeline, you fetch nothing here. And then, once you figure out the condition of the branch, you fetch from the target. In this case, branch is taken, apparently, right? So it takes 6 cycles to fetch all of these instructions in this code. Now, if you have a delayed branch, well, what can you do? You have let's say you have one instruction delay slot in the specified in your branch. Well, we would like to fill the delay slot. What can we fill it with? We cannot fill it with any of the instructions that come after the branch, because depending on the branch condition, you're going to execute either D or G. But look, there's an instruction here that doesn't affect the condition of the branch. So, and that doesn't affect also C. Right? Looks like it's independent. The branch is independent, and C is also independent of B, which means that you can move B to the delay slot. Right? That's what we did here. So B is going to be always executed, regardless of where the branch goes, and that gives you the same effect as executing this straight line code ABC. Right? Okay. So if you look at the timeline, the first cycle we fetch A, the next cycle we fetch C, the next cycle we fetch the conditional branch with the delay slot, and the next cycle we fetch the delay slot instruction, and in the next cycle, the branch takes effect, and we fetch from the target. Then this takes 5 cycles. Yes?
So you don't know whether it's a branch or not until the second stage. So how do you not load anything?
Well, okay. So in this case, I assumed a pipeline where you have fetch and execute. Right?
Okay.
So yeah, really what's happening is you're fetching and decoding, and then executing and storing result if you want. Actually, that's why this is for illustration. But here you don't need to know whether or not it's a branch, right? Because it's a delay slot instruction. You always execute the instruction that comes after the branch. That's the nice thing about the delayed branch. You don't need to know whether something is a branch or not. You're always going to execute the next instruction. Okay?
I'm very confused. So are these things reordered by the pipeline, or have they been already reordered by the
Compiler.
Okay.
Because it's the semantics of the instruction, right? The instruction says in the ISA, the instruction semantics is this branch takes effect only after the next instruction that comes in the code is executed. So this is the code that the compiler or the programmer generates. So what do you say? Basically, you say 1 cycle in this case, right? You didn't need to stall. And also, I mean, if you did branch prediction, in this case, you save the branch prediction hardware because you don't need to do branch prediction. So it's nice. Well, we'll see if it's nice later on. Right? So there's also the concept of delayed branch with squashing. Let's see if you can actually guess. In the Spark ISA, what the designers did was, if the branch actually falls through, if the branch is not taken, the delay slot instruction is not executed. So if the branch is taken, if the branch turns out to be taken, the delay slot instruction is always executed. But if the branch is not taken, the semantics of the branch is such that the delay slot instruction is not executed. Anybody guess why this could help? Yes?
You know, it's just replicate the instruction at the destination. You're there.
Yes, you could do that. That's right.
I was going to say something just like wherever you're going to jump, that's that instruction in the delay slot. And if we don't branch, then just use the support.
Exactly. So that if you don't jump to the target, then basically delay slot instruction has no effect. So you guys are getting at something. There's a common construct where you usually take the branch. It's a loop, right? So if you look at the loop, let's say this is your loop. This is your normal code. There's no delay slot here. And you have instructions like this, A, B, C, and conditional branch. They're all dependent. It's a dependence chain. And if the branch is taken, you will go back to the loop, and you'll keep executing the loop. If the branch is not taken, then you will go to the fall-through path. If you don't have delayed branch with squashing, there is no way the compiler can fill. Well, there may be ways, but at least there is no simple way in which the compiler or the programmer can fill this delay slot. Because what are you going to do? You cannot put D in the delay slot because if the branch is taken, you don't want to execute D. You cannot put A, B. You cannot put A in the delay slot because if the branch is not taken, then you don't want to execute A. Okay. So if the branch is taken, which means that the compiler cannot put anything here, so you get an OR in the delay slot. But if you had delayed branch with squashing, you could put A here, right? If the branch is taken, A will be executed. And since A is in the delay slot, it's already executed. If the branch is not taken, the instruction in the delay slot is squashed automatically. Does that make sense? So this is, in a sense, it's kind of like compiler-directed branch prediction. Right? You're squashing the instruction if the branch is not taken. But this enables the compiler to fill this delay slot more effectively when you have a loop like this. Okay? So this could get very complicated, actually. I don't want to go. What if you have a branch inside a delay slot? Right? And in some ISAs, do not even specify what happens in that case. So you shouldn't put a branch in the delay slot in some ISAs. Yes?
So is A executed twice though, even?
No. Right? So what I did was basically put...
Okay.
So the first time you go through the loop, you execute ABC. And this is the next iteration's A. Okay? And when you fall through, you don't execute A because you have squashing. Okay. Okay, so what are the advantages of this delayed branching? Well, obviously, I gave you the advantage. You keep the pipeline full with useful instructions. I guess useless instructions if you have an OAuth. Assuming the number of delay slots you have is the same as the number of instructions to keep the pipeline full before the branch resolves. Okay. Hopefully you will, there's a problem with this, and hopefully when I ask you the disadvantages, you'll reference that. And assuming you can fill all the delay slots with useful instructions. Right? So, I guess what is the problem? With a two-stage pipeline, you need to find only one instruction for the delay slot. Right? But what if your pipeline is 5 stages and your branch is resolved here? That means you now need to find 3 instructions to fill the delay slot. What if your pipeline in the future you want to clock your machine very fast? What if your pipeline is 30 stages? As it was in Intel Prescott, right? This is the 2nd generation Pentium. And if your, branch is resolved in the 25th stage. Do you redefine your branch instruction such that you have 24 delay slots? Now you see the problem, right? The key problem is, well, let me go back to that disadvantage. We've already covered this, but the key problem is you're not tying the ISA semantics to the hardware implementation. Because this delay slot was introduced because you have a pipeline processor and you don't want to predict the branch. Keep the hardware simple. Right? Because you can keep the pipeline full. If you have a 2-stage pipeline, you're always going to fetch the next instruction. And the compiler guarantees that that instruction is independent. It's great if your pipeline is always 2 stages, maybe. But your implementation, how many stages in your pipeline, you may want to change that over generations, right? And if you make your pipeline 30 stages, now your IC says your branch has only 1 instruction delay slot. Now your delay branching is useless, right? Because you can fill, you don't need to figure out where the branch goes for the next instruction, but what about the remaining ones? So you either need to change the semantics of your branch instruction with every implementation, which is terrible as you figured out because it breaks your backward compatibility. What happens if you try to execute code that was written for the previous generation? Right? You don't want to change your ISA with every implementation. Or you obey your ISA, which is the more reasonable thing to do. You don't change your ISA and you live with 1 delay slot, which is what these ISAs have been doing for, since they have been designed. And it becomes a nuisance for the hardware designer. So if you talk with people who design Spark processors, now it's designed by Oracle, or MIPS processors, they will tell you what kind of a headache this delay slot is. Because the delay slot in these ISAs is specified as a single instruction. The instruction that comes after the branch is always executed. But then, they don't have a 2-stage pipeline, they have a 10-stage pipeline, 20-stage pipeline. So delay slot maybe helps with filling the pipeline for one instruction, but for the remaining stages, they still need to keep the pipeline full. So they have to employ some other technique, which is branch prediction in most of these processors. Okay? Does this make sense? So this is a bad idea because it really ties the ISA semantics to the hardware implementation. Yes, you had a question?
This very small point I have. It's not as simple as this, but if you're squashing it, aren't we wasting some amount of memory? Because that instruction A twice.
Oh, I see. You mean in the second case?
It's a very small factor.
Yeah, it's good. But there may be other reasons why you replicate these instructions if you want to do compiler optimizations. Okay. So this is one disadvantage. The other disadvantage is it's not easy to fill the delay slots, even with a 2-stage pipeline. And it becomes worse as you increase the pipeline depth. And your number of delay slots should really be variable with variable latency. And this will become more clear when we talk about out-of-order execution. If you're executing instructions out of order, then this becomes even more of a nuisance because your branch resolution latency is not constant. Does that make sense? Because your branch is executed when its data values are available in an out-of-order execution machine. And this will become more clear. Which means that your branch is not simply executed after n cycles or after n stages. This n becomes variable, and now your delay slots need to be variable, which is almost impossible to do, right? Okay. So the advantage, you can keep the pipeline full without complicating the hardware, but there are significant disadvantages that makes this a bad idea. So in general, you don't want to tie the ISA semantics to hardware implementation. And this is one of these examples where this clean design rule is violated. Because if you tie the ISA semantics to the implementation, you cannot easily change the implementation. Or if you change the implementation, your ISA semantic features will become a headache on the hardware designer, because they still have to support it in the future, even though you don't gain benefit. Okay, so just as an aside, this is from your book, there are ways to fill the delay slot by doing compiler optimizations. You can reorder data-independent instructions in a way that doesn't change the program semantics. So for example, here, this is the example I gave in my animations, if you will. You have here you have the branch, and you have an instruction that's independent right before the branch. In that case, you can easily fill the delay slot with that instruction within the same basic block. But you can actually fill the delay slot with the instructions that are not necessarily in the same basic block. Do you know what basic block means? So a basic block is a sequence of instructions or a sequence of code basically when you enter with a single entry and a single exit point. Basically a code block, if you will, or a sequence of instructions with a single entry point and a single exit point. Which means that there is no branches within that sequence of code. Which means that when you enter this basic block, you're going to execute until the branch. You know for sure that you're going to execute, unless there are exceptions. until the branch. And then you have, usually basic blocks are terminated in the branch, and the branch can go multiple ways. So let's say you don't have independent instructions to fill the delay slot within this basic block. One thing you can do is, what if there are instructions that are here, right? Maybe you can fill the delay slot with the instructions that are here. Maybe there is an instruction that's executed on both paths. In that case, you can fill the delay slot. You can take that instruction, remove it from the target blocks, and place it in the delay slot. Because that instruction is going to be executed on both paths, regardless of where the branch goes. So that's one thing the compiler can do. So the compiler alternative, let's say this doesn't exist. This is a nice case, right? You have the same instruction on both paths. And of course, the same instruction should not be dependent on any instructions before it, because you have to obey the data dependencies. But let's say you don't have such an instruction. Let's say you still want to fill the delay slot. Maybe you pick an independent instruction here and place it into the delay slot. Now, if the branch goes this way, this instruction should have been executed. That's good, right? Let's say this is the taken path. In this case, this is from the target. At the target, you have this subtract instruction. Let's say you want to fill the delay slot with that subtract instruction. Well, if you do that, let me put the subtract instruction here. Basically, the compiler can move the subtract instruction here. What if the branch goes this way? Well, if you had delay branch with squashing, this would work nicely, right? So here, again, delay branch with squashing helps. That enables more opportunities to fill the delay slot. What if you didn't have delay branch with squashing? Well, then the compiler needs to ensure that the semantics of the program doesn't change. Which means that the subtract will be executed, but it shouldn't be executed if the branch is not taken. So what the compiler does is it inserts what is called an undo operation to this fall through path. And basically that undoes the effect of the subtract. Does that make sense? The compiler needs to preserve the semantics, and to fill the delay slot, it finds an independent instruction from one path. But if the branch goes the other way, then the compiler needs to ensure that that sequence of code correctly executes. Which means that you need to, I guess, undo the effect of the subtract. Make sense? Yes?
How's it work with stores?
So yeah, you got to be careful. That's right. So some things you cannot. That's the idea of safety. So some code movement like this is safe. Some other code movement is not safe. So if you actually put a store here, then you will need to store the old value again. But then you change the architectural semantics of the program in that case. So compiler doesn't move the stores that way. Okay? So not all code movements are possible. Only some instructions are movable. Again, you could do the same thing from the fall through path. Then you need to do undo operations in the target path, right? Taken path. Yes?
What are the disadvantages of squashing?
What are the disadvantages of squashing? Now it complicates your microarchitecture, right? The microarchitecture needs to obey that semantics. Remember, the nice thing about the delayed branch is assuming your pipeline fits the specification of the delayed branch, your microarchitecture doesn't need to do anything when it sees a branch. Right? Whereas if you have squashing, now the microarchitecture needs to squash this instruction if the branch is taken. So it's like a pipeline flush. You're really flushing your pipeline partially.
So it seems like you'll get less efficiency if you wouldn't wanted that instruction than in both cases, because now you're just leaving that one.
That's right. If you squash. Okay? Okay. You can all maybe we'll have a homework question on the delayed branching so that you can have fun with it. Okay. So fine-grained multithreading. This is another solution. Remember we covered this. I would like to cover this in a little bit more detail. We covered this when we talked about data dependencies, right? You can eliminate any kind of dependence by doing something else. And that something else was executing an instruction from a different thread. That's the idea of fine-grained multithreading. Hardware has multiple thread contexts. Each cycle, the fetch engine fetches from a different thread. So such that you never have an instruction in the pipeline from the same thread. Which means that you don't have the branch prediction problem or the data dependence problem. And this is an example here. While you're fetching an instruction from stream 3, stream is thread context, if you will, one thread. Another thread's instruction is fetching its operands, another thread's instruction is executing, maybe another thread's instruction is in another execute stage, another thread's instruction is storing its result. And this is a technique that has been used for a long time. So by the time the fetched branch resolves, there's no need to fetch another instruction from the same thread. So you've eliminated the problem. This is the idea of you're really overlapping the latency of the resolution of the branch with execution or fetching or processing of instructions from other threads. So this is a general technique for tolerating latency, if you will. Well, the good thing is there's no logic needed for control and data dependence handling within a thread. Right? You've eliminated all that complexity. What are the downsides? That's right. So now you need to, well, I guess I'll give you all of them. You need to have extra logic for keeping thread context. And what does that constitute? You have to have multiple register files for different threads. You have to have multiple program counters. Right? Yes?
When you say multiple thread contacts, is that like one processor and multiple threads? Or
That's right, yes. So one processor has multiple register files, one for each thread.
Okay. And there's just going to be one pipeline also, right?
That's right, a single pipeline. You can fetch from a different thread every cycle. So let me give you a more concrete picture of this. Let's say this is your pipeline fetch. Well, I'll expand on this. Decode, execute, write back. So how do you fetch? Well, let's say you have an iCache, and let's say you have 4 stages. You want to have 4 threads. What do you have? PC for thread 0. PC for thread 1. PC for thread 2. PC for thread 3. And you have a mux that determines what PC is used to access the instruction cache. And every cycle you rotate. The round robin selection of which thread you're going to fetch from. Well, there's another thing. Here, you have register file for thread 0. Register file for thread 1. I guess I omitted one register file in the space, but register file for thread. You have to have register files for each thread. And again, depending on which thread you fetched from in the previous cycle, you select which register file you're going to access. Now you see the hardware cost, right? You have 4 register files. Okay?
It doesn't necessarily improve throughput, does
It doesn't necessarily improve throughput. What do you mean? It does improve throughput, right? Assuming you have instructions in each thread, useful threads, 4 threads. You're always keeping your pipeline full, right? And there is no data dependency or control dependency that you need to worry about.
Doesn't help single task in terms of usage.
Yes, that's right. Single thread performance suffers, right? Because you're fetching from that thread every n cycles, if you will. Right? If you were fetching from only that thread, you would be, in the ideal case, finishing 1 instruction per cycle.
So overall throughput will increase in that case because you have more work.
That's right. Exactly.
It seems like it can be said of that in terms of virtual memory too, because what you're going to also, it seems bad from a CAN's perspective if you're always fetching.
That's right. So you're thinking deeply. Good. You can think of other disadvantages of these. There are other disadvantages, but there are other advantages also. Okay. And the other case where this doesn't help is what if you don't have enough thread context, right? And if you don't have enough thread context, then you insert no ops. Again, no ops is a solution to keep the hardware simple. But you lose two of them. Okay. But this is a powerful idea to eliminate complex logic, especially if your design point is a workload where you have many threads. You know that you're going to have many threads. Then you can design a very simple pipeline. Okay. So let's go to a solution where we don't degrade single thread performance. And that's the idea of branch prediction. So let me illustrate this a little bit. The idea is to guess the next instruction to fetch, right? So if you don't have branch prediction, in this code, this is what happens. When you get to the branch, you stall, and you fetch from the next instruction after, you fetch the next instruction, you know the next instruction after the branch is off. Whereas if you have branch prediction, you guess the direction. In this case, we guess add will come after branch. This is when we fetch the branch. And we keep fetching. So you can improve performance significantly assuming you're correct. Right? In this case, it was 12 cycles, goes to 8 cycles. You can do this on your own. Well, what if you're wrong? Then you have a problem, right? If you're wrong, this is the case where the pipeline is full here. The next instruction was predicted to be this add, but what if it needed to be this load? Then you need to flush the pipeline. Does that make sense? This is called a pipeline flush. Flush means if the next instruction is not the instruction that the branch really branches to, then you need to ensure that the instructions that are on the wrong path, the instructions that you fetched incorrectly, these are instructions on the wrong path, if you will, wrong path of the branch, or mispredicted path. You need to ensure that you don't update the state of the machine. So what do? Basically, you implement a pipeline flush. And how do you implement the pipeline flush? Well, remember the valve bits in your pipeline? When the branch is resolved, and if the target, if the direction of the branch did not match the direction that you predicted when you fetched the branch, you set the valve bits to all 0. Right? All the valve bits in these pipeline stages, after the branch is resolved, is set to 0. That's one way of implementing flush. Okay? And you fetch from the correct target later on. Okay. So this is a more modern pipeline, just to give you an idea. Basic idea is to guess the next instruction when a branch is fetched. So let's look at this code. You have a branch here that could go to basic block 1 or basic block 3. When you fetch this branch, let's say these are single instructions, if you will. They're not, but just to illustrate. You have the question what to fetch next. Well, if you can predict, let's say the branch will go this way. And you keep fetching. And when the branch actually executes, you verify the prediction. What is verifying the prediction? Did I predict correctly? Because now you know the outcome of the branch. You check whether the outcome actually matches your prediction. Well, if it doesn't match, then you flush everything that came after the branch. You fill the pipeline, but now you're going to flush it and fetch from the correct target. If it matches, then you don't need to flush. You can keep going. Right? Make sense? Yes?
Do we need extra cycles to undo what you wrote?
Undo.
Safety perspective, if you change something.
Okay, what is change something? Remember, in the pipeline, we're always changing the memory or the or the registers at the very end. Right? There's a store results stage. Okay? Okay? But that's the basic pipeline. The existing processors are much more complicated. So your question is valid. But we haven't got to the existing processors. Okay? We have gone to processors where you actually change something. Okay. Is this clear? That's the basic idea. Yes?
Please repeat. So before this, what happens if you take the incorrect branch?
What happens if you what?
If you take the incorrect branch?
Incorrect branch. Incorrect path?
Yes, this one.
Yeah. So you predict that you're going to fetch from V1, and you fill the pipeline, right? And there are instructions that are coming after that, of course, that I didn't show. And when the branch is executed, you check whether the target should have been V1. When the branch is executed, you know whether the next instruction is at V1 or V3, right? So you check the next program counter that the branch specifies. If it is the same as the program counter that you predicted when the branch was fetched, then this is good. You can keep going, keep fetching, because you're on the correct path. You did the correct thing. Whereas if it should have been V3, now you need to flush and refetch from V3. Okay? Well, let's assume the simplest way of doing branch prediction is you always predict the next instruction is PC plus 4, right? Even if you have a control flow instruction. And at the LU stage, you check whether that's a correct prediction. And if it's incorrect, basically when a branch is resolved, all wrong path instructions are flushed. This is another example of this. So how do you do that? Basically, you kill the instructions that come after the branch. So what does this mean? This means that if you guess correctly, there is no penalty, right? You can keep fetching. And you kept the pipeline full. And remember, 86% of the time, this is average number that we came up with earlier. 86% of the time you'll be correct. If you're incorrect, then in this case you have two bubbles, two cycles, because you flushed two instructions. Let's do the calculation. If we assume no data dependencies, there should be dependencies, and 20% control flow instructions, and 70% of control flow instructions are taken, what is your cycle per instruction? Well, normally, you definitely spend one cycle per instruction. If you have no data dependency problems or control dependency problems, you should be finishing one instruction in one cycle. That should be your throughput in the pipeline. But now you have additional cycles, if you will. Now what are those additional cycles? Well, 20% of the time you have a branch, and 70% of those branches are taken, right? Which means that you mispredict, I guess this is 14% of all instructions, and when you mispredict, you pay a 2-cycle penalty. Does that make sense? So 14% of the time, you lose 2 slots in your pipeline, which means that your CPI increases by 28%. So you lost performance by that much, because of these mispredictions. Okay. Make sense? So what is this? This is the probability of a wrong guess, if you will. Probability of a misprediction. This is also called misprediction rate. Well, that's misprediction rate across all instructions. Your misprediction rate across all branches is 70%, right? But 20% of all instructions is is a branch. And this is called the misprediction penalty. This is the penalty for a wrong guess. Whenever you mispredict, you lose 2 slots in your pipeline because you need to flush 2 instructions. So you can improve performance by improving either of these. You can reduce this penalty for wrong guess. potentially, if you can resolve your branch early in the pipeline instead of waiting until the ALU stage. Right? Can you do that?
With additional hardware.
There you go, with additional hardware. Let's take a look at if we can do it. Well, with additional hardware you can do it, that's right. Well, in this case, let me highlight the hardware. So instead of resolving the branch at the end of this ALU stage, we add additional hardware to calculate the target address here. And also, remember in MIPS, you simply compare two registers, right, to check whether the branch is taken or not taken. So after you access your register file, you add a comparator to determine the branch condition. So now this reduces your pipeline flush penalty by 1 cycle. And your CPI, if you do the calculation, we reduce this from 2 to 1, goes down to 1.14. Is this a good idea? How many people say, yes, this is a good idea? Quite a few. Who says this is a bad idea?
Maybe because now you have a longer path.
That's right.
And you're
Exactly. So the right answer to the question is it depends. Maybe. Why? Remember, well, is it still here? There you go. It's over there. So important that it's bubbled up to the top. So we reduced CPI, right? It became, before it was 1.28, now it's 1.14. But we potentially did something bad to this. Right? Why? Before, we didn't have this comparator after the register file. But now we have to compare two registers, determine the condition of the branch, and select the right input to the program counter based on that condition. And this could lengthen the critical path. If the critical path is lengthened because of this, now your clock cycle time increases potentially, right? Yes?
So, is it a bad assumption to make that the critical path is going to be around the battery?
Well, that depends, right? That depends on the design.
In a normal processor that we have.
Remember, we discussed this. There could be many places where the critical path can happen. But if you lengthen your critical path unreasonably, your critical path can be anywhere, right? It could be, I mean, if you add 10 ALUs here, you increase your critical path significantly, right? And it could be that your memory is just a little bit slower than your register file, and that was your critical path, but because you added the subtractor logic here, now that became your critical path. And if the increase in critical path is more than 14%, you're losing performance. Right? Yes?
Well, we've already seen that it can be in the execute stage because the multiplier was slowing us down in the previous
lab, yeah. So it could be anywhere, really. It depends on your pipeline. I'm sorry?
That was like combination. I mean,
well, again, it depends.
Right.
You cannot say the critical path is in memory. Remember, it could be a control store, right? If you design something. So you have to balance your pipeline. Okay. So, enhanced branch prediction. This was a simple branch prediction. We're predicting PC plus 4. But we want to do better without increasing our critical path, hopefully. Basically, we want to predict the next fetch address to be used in the next cycle. This really requires three things to be predicted, right? One is whether the fetch instruction is a branch, and we'll get to this. What is the direction of the branch, if the branch is conditional, and we're going to assume that the branches are conditional in this case from now on. We'll get back to branches that are not conditional later on. And what is the target of the address of the branch? We're going to use this if the branch is taken. If the branch is not taken, then it's PC plus 4. Yes?
I had a question about the previous thing. Could you possibly, like, before your branch resolution has been done yearly, right?
Okay.
Could you direct just forward data to it instead?
Forward data to it. To what? To the ALU?
Yeah.
I don't understand how that would work. Think about it. Okay. So you really need these three things available to you at the fetch stage to be able to predict the branch, other than predicting PC plus 4, right? So I guess one question is, how do you get the branch target address? So you're in the fetch stage. We have another one here. Oh, there was one more hiding. Yeah. Okay, I'll do it here. You have your iCache, and you have your program counter. In the next cycle, you want to figure out what your program counter is. And if the branch is taken, you would like this program counter to be the target address, right? If you predict the branch to be taken, this should be the target address. So where do you get the target address? The target address, you haven't fetched the instruction yet. Right? Well, there's one observation, and the observation is that target addresses remain the same for a conditional direct branch across different dynamic instances, assuming the target address is computed as program counter plus offset. Right? The program counter of the branch doesn't change. The offset doesn't change because it's in the instruction bytes. Which means that if you remember what your target was the previous time you executed this branch and record it somewhere, the next time you come to this PC program counter, you can get that target from somewhere. That's the idea of a branch target buffer. It's essentially a buffer that's indexed by the program counter, and it gives you the target address. Does that make sense? The first time you execute the branch, you record the target address there, such that the next time you come to that PC, you know the target. But when you execute this branch the first time, you don't have the target. Okay? That's the idea. Store the target address from previous instance and access it with the program counter. Branch target buffer or branch target address cache. Yes?
Would you have to do a comparison in this case?
Comparison in this case. Compare which one?
Compare the target address again to make sure that it's not changed at any time.
So, assuming your target address is computed this way, it should not change, right?
What if something in the code caused the offset to be changed?
Okay, so are you getting into self-modifying code? If you have self-modifying code, yes, that will change. That will change whether or not this is a branch either. But you will do that comparison anyway. When you execute the branch, you will check whether the target you should go to is the same as the target you fetched. So you will eventually do that comparison. Okay? But that's a good point. I mean, if you have self-modifying code, even this assumption is not correct. But you're already falling back to misprediction recovery anyway. Okay. Okay, so let's take a look at the fetch stage, a general fetch stage, where we actually predict the branches, conditional branches. This is a cache of target addresses, which is branch target buffer that I showed here. And I don't show the iCache here. iCache is also accessed in parallel here. And we also have a direction predictor. And I'll call it 2-bit counters, and this will become clear soon. With the address of the current branch, program counter, we access the branch target buffer. This gives us a target address, but you may not hit in this branch target buffer. Right? Why? Because you may not have seen this branch before. So what does this access look like? We will see how a cache operates later. For now, you just need to know that this is your program counter. Let's say it's 32 bits. With some number of bits, you index into a memory structure called BTB. And BTB essentially contains two things. One is the tag, if you will, and the other is the target. And what is this tag? Let's say this is n bits. This tag is which top n bits of the program counter is this target associated with. If these two n bits match, then you have the target for that program counter. So it's an associative memory. Does that make sense? In the extreme case, these m bits are the length of the program counter, such that you compare every single entry in this buffer to the program counter, and if you have a match, then you have the target. You studied content-associated memories, content-addressable memories, right? Essentially, you're addressing this memory with the program counter's content. And if you have a match for that program counter, then you have the target. If you don't have a match, then this is a miss. You don't get a hit in this branch target buffer. Yes?
Does your BTB have to be really big to have most non-tables?
So yes, we'll get back to it. We'll get back to that. If there are misses, then you have to replace something. Okay, let's assume that this is good for now. Okay. Concurrently with the program counter, you access a prediction mechanism, direction predictor, that tells you whether the branch should be taken or not taken. That's a direction prediction. So you're predicting the target address, you're also predicting the direction. Now if the branch is taken and the BTB gave you a target address, then the next fetch address should be the target address. If the branch is not taken, or BTB was a miss, BTB did not give you a target address, then the next fetch address should be program counter plus instruction size. Then you go to the fall-through address. And that's your predicted next fetch address. Does that make sense? So you predict the direction, predict the target, and pick the target or PC plus 4, let's say, as your next fetch address, depending on your prediction. And we'll see, well, let's assume that in this case, we have, we're doing always taken. Now in this case, you can have a predictor that, we'll look at how to design this predictor. But let's say this predictor says always taken, which means that you don't have 2-bit counters. You just always predict it as taken. If that's the case, now, and assume that this is perfect, your cycles per instruction can be reduced significantly. If 70% of your branches are taken, you mispredict the branch 30% of the time, and 20% of your instructions are branches, so you get a penalty, 2-cycle penalty, 12% of the time. Well, you get a 2-cycle penalty 6% of the time, so your CPI is 1.12. Remember, contrast this with not that one, because that would increase the clock cycle time, right? Oh. We're this far away? Is that true? Let's see. I think we had 1.28, right? There you go. Yes. Contrast this with 1.28. This was when you predict not taken. So we're predicting taken now, and we are able to predict taken because now we have the target address in the cycle we fetch the instruction. Okay. So that's the idea of branch direction prediction. You can have more sophisticated direction predictors, and we will see these later on. Don't worry about that now. Okay. Now let's go through how you can actually predict these branches. We looked at always not taken. We looked at always taken. There are other ways of doing this. And these are called static branch prediction, or compile time, if you will, because the prediction that you make doesn't change during runtime. If you look at a branch, the prediction, you can tell the prediction, basically. That's what compile time or static branch prediction means. But always not taken, obviously. The advantage of this is it's simple to implement. There's no need for BTB, right? If you're always not taken. And there's no need for direction prediction. Well, that's true for this also. But you get low accuracy, 40%. And in the calculations, we had 30%. Right? But the good thing about always not taken is maybe the compiler can lay out the code such that the likely path is the not taken path. Right? Remember, we discussed this early in one of the lectures. We talked about profile-guided code positioning paper. That's the idea. If the compiler can do that optimization, and it may not be easy to do when you have loops, then maybe you can improve the accuracy of this. Always taken is usually more accurate because backward branches are usually taken. So you get better accuracy. So because of this observation, people observe that backward branches are usually taken and forward branches are slightly not taken. This is empirical. So some processes employ backward branches taken, forward branches not taken as a prediction mechanism. Does that make sense? And you know whether the branch is backward or not by checking if the target address is lower than the branch program count. Right? So this has better accuracy. But that's not the only way of doing things. There are more interesting approaches. One approach is profile-based. So what if the compiler profiles the code, runs it with representative input sets, and for each branch determines the likely direction given that input set. And there is a single bit in the branch instruction, encoding of the branch, encoding, that says if this bit is set 0, then the branch is not taken, likely not taken, predicted not taken, otherwise predicted and taken. So some bit in the branch instruction gives you the prediction, and the compiler sets that bit, or the programmer. Well, this is nice because now you get per branch prediction, right? For each branch, the compiler can set this bit differently. Make sense? Based on the profile behavior. Of course, the downsides are also many. Well, you get more accurate prediction schemes, assuming your profile behavior again matches your runtime behavior. And we discussed this a lot earlier in the course. The downside is now you're changing your ISA, if you will. It requires hint bits in the branch instruction format. But most ISAs today have these hint bits. You can specify whether the branch is likely not taken or taken in the compiler. The accuracy again depends on dynamic branch behavior. Yes?
How would the compiler do this? The ISAs, like the MIPS ISA has a branch likely, a couple branch likely, but how does a compiler know if something's likely or not?
Okay, so it uses profiling. The idea is the programmer gives some input sets, and the compiler runs those input sets, and every time it sees a branch, it records how many times was this branch taken or not taken, and based on that sets the bit. If the branch is taken 99% of the time, for example, with those input sets, it sets the bit as likely taken. Okay, so accuracy depends on dynamic branch behavior, right? If your dynamic branch behavior is like this, or like this, you get 50% accuracy, regardless of what you set the bit to. But if you look at this is a really predictable pattern, right? If you had just some dynamic information, for example, well, what could that dynamic information be? You recorded what the direction was for the branch the last time you saw the branch, you executed the branch. Then you would get really good accuracy here, right? Except for the transition here. That's the downside of static branch prediction. It doesn't get good accuracy here. Again, here, if you can find out this pattern dynamically in hardware, you can get 100% accuracy here, right? Like, barring the boundary conditions. Because you always flip the prediction every other time you fetch the branch. Question is, how can you figure out these patterns? So these branches, you should really be able to get 100% accuracy with a simple hardware scheme. And that's the idea of dynamic branch prediction that we will examine. Okay? So accuracy depends on the representative of the profile input set also. For example, you can have a perfectly predictable branch. It's always taken when you run it. But because your profile input set was not representative, you can predict it always not taken. And you can get 0% accuracy. Okay. So dynamic branch prediction, the idea is to predict these cases where you actually have very good predictability that the compiler cannot recognize because you have a single prediction for every instance of the branch. Dynamic branch prediction means for each different instance, based on information that you collect while the program is running, you can make a different prediction. Let's see how we do that. Well, the key idea is predict the branch based on dynamic information collected at runtime. Advantages, first of all, this eliminates the need for profiling, right? There is no need for profiling. Second, the prediction is based on history of the execution of the branch. You can adapt to dynamic changes in branch behavior like this. The disadvantage now you will see will require more complex hardware. Well, the first simplest dynamic branch prediction mechanism is last time predictor. Basically, you have a single bit per branch. You can store it in the BTB, if you will, or you can store it separately in the direction predictor I showed you. This indicates which direction branch went last time it was executed. And in this case, you'll get 90% accuracy, right? Why? Well, let's assume that you start out predicting the branch taken. You'll be correct until here. And when the branch is executed next, you'll predict it as, well, let me explain you what this is. This is basically the execution history of the branch. The first time it's executed, it's taken, next time it's taken, next time it's taken, next time it's taken. I think at the end of the 10th execution, it's still taken. The 11th time, it's not taken. Okay? If you start out by predicting the branch as taken, you'll be correct until this point. When the next time you predict the processor will predict the branch as taken, but the actual outcome will be not taken, which means that you mispredicted. So you lost one prediction is incorrect. And the next time, you will predict this as, well, what will you predict that as? You'll predict that as not taken. Now, why do we have 90% accuracy here? Did I make a mistake? Yeah, it should be 95 then, right?
Maybe you assume the first one.
Yeah, if you assume, depends on what you assume. Maybe I assumed here that you start out predicting not taken. That's possible. But actually, starting out predicting taken is a better idea, right? If most of your branches are taken. Okay, so that was the assumption probably here. But it should be 95% accuracy if you start out predicting as taken. Okay, so the downside of this is, this always mispredicts the last iteration and the first iteration of the branch, of a loop branch. Because if you think about a loop branch, you have a branch that goes this way, and this is the loop body. And let's say this loop executes, and when you execute, assuming that the first iteration is correct, when you fall through the loop the first time, you mispredict, because the prediction is biased to taken, but this needs to go, you're falling through the loop, so it's not taken. The next time you come to the loop, let's say there's an outer loop here, you come to the loop, you execute the loop again, you come to the branch, you mispredict because the last time you executed this loop, you went fall through, which is not taken. But you should go taken this time, assuming the loop is biased toward taken. Make sense? So you mispredict the first time you exit the loop, and you mispredict the first instance of the first iteration of the loop. So you mispredict twice. And if the loop is, well, if you have a loop branch with a large number of iterations, well, let's get back to that. If you, well, maybe I should answer that call, huh? Is this the matrix or? I'll wait for a couple more rings. Are you guys calling? Maybe somebody's going to ask about the loop branches. Okay, I'll do that. Telemarketer. I'm glad it wasn't any of you. Okay. So if you look at a loop branch with a large number of iterations, let's say you get 85% accuracy with this kind of prediction mechanism, last time prediction mechanism. Well, actually, this is misplaced. This is good for a loop branch with a large number of iterations, right? You'll almost always, if this loop iterates 1 million times, your prediction accuracy will be, I guess, 1 million minus 2 divided by 1 million, right? That's almost 100%. Let's ignore this case. I'll get back to that. But if you have loop branches with small number of iterations, for loops with small number of iterations, you can have 0% accuracy. This is you execute the loop once and then fall through the next time. Execute the loop once, fall through the next time. This is bad. So this I should have put it over here. But let's say you get 85% accuracy with this predictor. Now you've reduced your CPI to 1.06. Now you can see your performance improves significantly. And ideally, you would get 1 CPI, right? Okay. So how do you implement the last time predictor? This is pretty simple. This is the picture I showed you here. You index your BTV. You match the tag if there's a target address here. Basically, you have 1 bit stored with each entry in your branch target buffer that tells whether the branch is taken or not taken the last time it was executed. So you can embed these prediction bits, last time prediction, into your BTV. Does that make sense? So you can study this. Okay. So this is your state machine for the last time predictor, if you will. You have 1 bit, 2 states. Let's say you start with predicting taken. If the branch is actually taken, you stay in this state. If the branch is actually not taken, when you resolve the branch, you change this bit in the this is actually branch history table. We will see this in more detail later. You change the bit to predict not taken. Let's say 0. And you can complete the state diagram, right? If you're predicted not taken and the branch is actually taken, you go to predicted taken state. Well, what was the problem with the last time predictor? It changed its prediction from taken to not taken or not taken to taken very quickly, right? With 1 incorrect outcome, incorrect prediction, you change your mind. And that's why we mispredicted the loop twice. If we didn't change our minds quickly here, the next time we come to the loop, we would predict the branch is taken. So we would get one less misprediction. Right? So that's what we're going to try to do. Yes?
When you have to write back, technically you have to know the PC of your present branch instruction several ways down in the pipeline. Plus, don't you also have to come back with the new PC that's trying to access the BTV for the next one? So doesn't that cause a conflict for the resource?
Yes, again, that's a resource conflict. So if you have a read port and a write port to your BTV, then you don't have a problem. Okay. Yeah, you need to multi-port your BTV in that case. Okay. Yeah, even though the branch may be mostly taken or mostly not taken, you change your mind quickly. So the solution is you add hysteresis to the predictor so that the prediction does not change on a single different outcome. You guys know the concept of hysteresis? Basically, you add some, I won't call it buffering, but some lag, if you will, before you change your prediction. You want to see incorrect prediction again before you change your mind. So we'll see how you do that. Basically, we use 2 bits to track the history of prediction for a branch instead of a single bit. So if you have 2 bits, then you have 4 states, right? 0, 0, 0, 1, 1, 0, 1, 1. And you can say these are the taken states and these are the not taken states. And you can, let's say you start from here. The first time you see the branch to be not taken, you move to the weakly taken state, if you will. And the next time you come to the branch, you'll predict it as taken. You didn't change your mind. You change your mind only at the boundary here. If you see another not taken outcome, then you change your mind. Right? So in this case, to change your mind for a branch, you need 2 consecutive predictions in the same direction. Okay. Basically, that's the idea. You can have 2 states for taken or not taken instead of 1 state for each. And this is a seminal paper that describes some of these ideas. Take a look at it if you're interested. It's a very clearly written paper. So that's the idea of 2-bit counter-based prediction. Each branch is associated with a 2-bit counter. And a strong prediction does not change with one single different outcome. So if you look at the accuracy for a loop with n iterations, your accuracy is n minus 1. Because you don't change your mind when you fall through. The next time you come, you're going to predict this branch to be taken. Now, if this seemingly hard case, you'll get 50% accuracy here, right? Let's assume initially you start with a weakly not taken state, and I'll show you what that is soon. You predicted not taken, weakly taken state. You predicted taken first. The next time, which will be correct, and you will go to the strongly taken state. The next time, even though the outcome is not taken, you will keep predicting this branch as taken. Right? So only 50% of the time you'll be wrong. So you get better prediction accuracy, but more hardware cost. Right? Now you have 2 bits per branch instead of 1 bit per branch. So if you look at this, this is essentially a counter that gives saturating arithmetic, right? You guys know about saturating arithmetic? Basically, you have a minimum and a maximum value in the arithmetic, and if you want to increment beyond the maximum value, you stay at the maximum value. And if you want to decrement beyond the minimum value, you stay at the minimum value. And that's what this is. It's essentially a saturating counter. Okay? So you have 2 states that are for predicted taken and 2 states for predicted not taken. And these are transitions. Essentially, if the branch is actually taken, you stay at the predicted taken state. And if it's actually not taken, you go to the weakly taken state, if you will. And if you see another outcome that's not taken, then you go to the weakly not taken state. So you can divide your state space like this. This is the strongly taken state. When you see a non-conforming outcome not taken, you will still predict the next instance as taken, but you will go to a different state. In the sense that this is weakly taken. Does that make sense? You can study this diagram, but it's pretty simple. And you can imagine, so the benefit of this is your prediction changed only after 2 consecutive mistakes. Right? You can imagine having more bits, right? What if you had 3 bits in your counter? Now you have 8 states. Right? That way, you change your mind even less quick. What if you had, 10 bits? You have 1,024 states. Exactly. So, as you increase the number of bits, then you become less adaptive, if you will. You change your mind. You have to see more evidence toward some other direction to change the prediction. Now, that may be good or bad. In this case, it may be good if you really should not change your mind, right? But it's bad if you take too long to change your mind. Does that make sense? In a sense, you're looking at you can think of this as evidence of whether the branch started doing something different. Okay. Let me see what time it is first. Well, looks like let's not take a break today. Because it's already 2:05, but hopefully you're having fun looking at the branch problem, and I'll ask you a question. So this is the branch problem. Let me restate it a little bit, because the problem is actually bigger than what we've described, and there is a reason. Well, you don't know the next fetch address after n cycles in a pipeline processor. Stalling on a branch wastes instruction processing bandwidth, and actually you're wasting slots. Not n instruction slots, but if you consider the processors to be superscalar, which we will get into in more detail in one of the later classes, what we have is really not this. Fetch, decode, execute. Now let's say actually this is longer. Let's say your branch, your branch resolves here. Resolve branch. You're wasting this. But if you're superscalar, meaning you're fetching multiple instructions, and and executing multiple instructions, which means that you really have multiple pipelines, if you will. You're really fetching a lot more, right? If this is your fetch width, and a good fetch width today is 4 instructions per cycle, for example. A lot of Intel processors can fetch 4 instructions per cycle. And this is your pipeline depth. And a good one may be, let's say, 15 or 20. You're really wasting 15 times 4, 60 instructions. Right? What a misprediction. And as your pipeline depth increases and fetch width increases, you're wasting more. So you're really wasting n times issue width, if you will, instruction slots. Well, let's see how bad this could be. Assume your fetch width is 5. You have 5 byte superscalar pipeline, and your pipeline depth is 20. You resolve a branch after 20 cycles. Let's just do the exercise of how long does it take to fetch 500 instructions. Let's say all you need is to fetch 500 instructions. And let's assume there are no fetch breaks, meaning you always have one branch instruction in the 5 instructions that you're trying to fetch. And 1 out of 5 instructions is a branch. And they're nicely uniformly distributed, if you will. If you have 100% accuracy, what is the answer? Well, we have 500 instructions to fetch, and we're fetching 5 instructions per cycle. And we're always accurate. 100 cycles, exactly. All instructions are fetched on the correct path, and no wasted work. Let's say we're pretty good, 99% accurate. Actually, very good, right? How many cycles does it take to fetch? Under 20 cycles, right? Why? Well, because 100 cycles to fetch all of the correct instructions, correct path instructions, you have to fetch them. But 1 out of 100 branches, you waste 20 cycles, right? And how many branches are there? Well, there are 100 branches. So once you waste 20 cycles. So now you're spending 120 cycles to do the same amount of work. And you fetch 20% extra instructions, right? So there's a cost to power as well. You're going to flush all those instructions, useless work. Now if you're 98% accurate, now 2 out of the 100 branches you fetch, because in these 500 instructions you have 100 branches, 2 of them are incorrect, so you're taking 140 cycles, and the extra work you do is really 40%. Now if you're 95% accurate, which is still pretty good, right? 95%. Think about it. Now you're spending 200 cycles fetching instructions instead of 100 cycles. So you've held your performance, even if you're 95% accurate. And you're doing 100% extra work. So that's the importance of this problem. As you make your processor more powerful by increasing your fetch width, how many instructions you can fetch, and more powerful by increasing your pipeline depth so that you have a higher clock frequency, this branch prediction becomes a lot more important, even if you have 95% accuracy, which is actually very good. You're really wasting half of your time and half of your energy by doing things that you don't want to do. Make sense? So this puts things into context. Before we were looking at only a 5-stage pipeline with a single white fetch. Maybe it didn't seem that important, but existing processors are like this. Okay, so can we do better? This is the reason I didn't want to stop, because I want you to look at if we can do better. So these predictors exploit last time predictability, if you will. But people have realized different things to improve upon this. One realization is that a branch's outcome can be correlated with past branches' outcomes. So because this is such an important problem, We want to improve the accuracy. So can we do something better? That's the idea of global branch correlation. The second realization was a branch's outcome can be correlated with the past outcomes of the same branch, not just the last outcome. Okay. What if the branch had a pattern, if you will? Taken, 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 not taken. Taken, 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 not taken. Taken, 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 not taken. Why could that happen? Well, if you have a for loop where the boundary condition is 3, right? This, right? Well, I like writing all over the place, but if you have code like this, I less than 3, I plus plus. Double what? Yeah, and if you have another for loop outside that, yeah, exactly. Then this will be taken, 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 not taken. And then you'll come back. Taken, 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 not taken. Taken, 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 not taken. Okay. So can you recognize this pattern? You can recognize this pattern if you realize this, right? This branch's outcomes are actually correlated with itself. And if you can record the history of this branch, such that, well, actually, let me give you the idea of local branch correlation. The idea is you have the history of the branch recorded. For this branch, you keep track of what were the last 4 outcomes. If it's 1, 1, 1, 0, you know that the next one should be 1. If it's 1, 1, 0, 1, you know that the next one should be 1. If it's 1, 0, 1, 1, the next time it should be 1. If it's 0, 1, 1, 1, then the next time it should be 0. This is the idea of a local history. For the branch, you keep track of the last n outcomes for that particular branch, and your prediction is based on what was the outcome when you last saw this history for this branch. Does that make sense? And there's a reason why it works, because the program constructs are like this. It's not magic. It's not black magic. Well, some of the branch predictors that have been proposed seem like black magic, actually, but this is a phenomenon in programs. Okay, we will get to this, but let's take a look at the global branch correlation. This may be less obvious to you guys. Different branch outcomes are actually correlated to each other. Well, that's what this says. Recently executed branch outcomes and the execution path are correlated with the outcome of the next branch. Well, you've all written code like this, perhaps, right? If condition 1 do something, if condition 1 and condition 2 do something. You know that if the first branch is not taken, then the second is also not taken. Right? So maybe you can exploit this correlation. Again, if condition 1, a equals 2, and then you branch on if a is equal to 0. But you know if the first branch is taken, then the second definitely not taken. Well, there are other things, more complicated. If condition 1 do something, if condition 2 do something, and if both conditions are true, do something else. Now you know information again here. If y and z are both taken, then x is also taken. If y and z are not taken, then x is also not taken. And there are programs. This is one of the famous programs. SPEC is the benchmark suite from Standard Performance Evaluation Corporation that many manufacturers test their microprocessors with. These are microprocessors are benchmarked using this suite. And this was a very hard to predict branch in the SPEC suite until people figured out global branch correlation. So if you look at this, what this code does is if A is equal to 2, it sets AA to 0. If BB is equal to 2, it sets BB equal to 0. And branches on AA is not equal to BB. And this is real code. I think this, I don't remember what the equivalent top does. I think it's actually it's a logic minimizer, I think, but I'm not sure. Well, obviously you see that there's correlation here, right? If B1 is not taken and B2 is not taken, then B3 is certainly taken. Is that correct? That's right. So how do you capture this global branch correlation? The idea is to associate branch outcomes with global taken or not taken history of all branches. and make a prediction based on the outcomes of the branch the last time the same global branch history was encountered. So basically, you keep track of the global history of all branches in a register, taken, not taken history, and you can encode the taken, not taken history with ones and zeros. 1, 0, 1, 1, 1, 1, 1, 0. Last seen branch was not taken. The previously seen branch was taken. Previously seen branch taken. Previously seen branch taken. Previously seen branch taken. And you can keep track of, I guess this is 3, 8. You can add one more if you will. 8 previous branches. And use this global history register to index into a table that recorded the outcome that was seen for this particular history before. This is called the pattern history table. And this is the idea of global history and branch predictor. Essentially, it uses 2 levels of history. So let's take a look at how this works. Basically, first level is you have this global branch history register that recorded the outcomes of the last n branches, last n seen branches. Direction of last n branches. The second level is the table of saturating counters we had seen before. The last time we saw this history, was the branch taken or not taken? You could have 1 bit, you could have 2 bits again. The direction the branch took the last time, the same history was seen. It could be this, right? And I guess I've already given you, well, you could look at this also. But, so this is implemented in Intel Pentium Pro. This was the first, so these are all real predictors, and we will see that the local one is real also. Pentium Pro had a 4-bit global history register, like this, and it had multiple pattern history tables. Basically, the way it was implemented was like this. I guess maybe I should start erasing some things. I'll just give you the Pentium Pro branch predictor, and then we'll part. Basically, it had a 4-bit history register, global history register, and using this, you would index, there were 4 different tables, pattern history tables of 2-bit counters. And this register was used to index into every one of them. And you would have a mux that would select which of these pattern history tables, 2-bit counters, to pick. And this was based on the program counter of the branch. Well, basically you would take 2 bits of the program counter. Basically, when I saw this history the last time, was the outcome taken or not taken? And that outcome is classified based on the program counter. Of course, you cannot have a table for each program counter, right? That would be a huge hardware. So you really divide the program counter into sets, if you will. So for this set of program counters, when I saw this history the last time, was the outcome taken or not taken? First level of history, second level of history. This is global, and this is what happened when you saw that global history last time. This way you can exploit that correlation across different branches and get much better prediction accuracy than the last time predictor. Yes, I'll take one question and then I'll let you go.
One of the bigger table is just last time prediction.
Well, if it's one bit, yes, it's last time. If it's 2 bits, last time with hysteresis. Okay, you asked also.
Yeah. Is there any way for hardware to predict, like, these are branch prediction, right? But there's also like switch statements and jump tables. And
so we will briefly cover that next time, but there are ways of doing that. Okay? All right. Make sure you read the paper in the sign for next time.